We previously learned that another term for a homogeneous mixture is a solution. A solution is made up of two components, the solute, which is usually present in smaller amounts. The solute is the substance that we are trying to dissolve, and the solvent. The solvent is present in a larger amount, and it's usually the medium that is doing the dissolving. In most of the solutions in this class, our solvent will usually be water, meaning that our solutions are called aqueous, which has the abbreviation AQ. That tells us that something is dissolved in water. When we talk about the concentration of a solution, we're talking about the ratio of solute to solvent. In a very concentrated solution, such as the example on the left in dark blue, there's going to be many solute particles to every solvent particle. On the dilute solution on the right-hand side, there's far less solute particles to every solvent particle, hence it appears as a lighter color. Calling something concentrated or dilute doesn't give us an actual description of its concentration, though. It doesn't tell us anything about the concentration numerically. They're just relative terms to one another. We'll use the term molarity in chemistry, with the abbreviation capital M, to express concentration from here on forward. The molarity of a solution is defined as the moles of solute per liter of solution. So it's important that we distinguish between the solute particles and the solvent particles. Molarity can be expressed in units of moles over liter or simply with a capital M. Let's use our new definition of molarity to practice calculating it. A student prepared a solution of sodium chloride by dissolving 1.461 grams of NaCl in enough water to make 250 milliliters of solution. What is the molarity of the solution? We just learned that molarity was defined as the moles of solute per liter of solution. So it's important that we're able to identify what our solute and solvent are in this case. So we're dissolving sodium chloride. So NaCl must be our solute, and we're dissolving it in water. So water must be the solvent. When we combine the two, the solute and the solvent, we make 250 milliliters total solution. So in order to calculate molarity, we need to figure out what our moles of sodium chloride are, and then divide by our total volume in liters. We have 1.461 grams of NaCl, and in order to convert our grams into moles, we'll have to determine the molar mass. 1 mole of NaCl is 55.85 grams. That would give us just the number of moles. Lastly, we have to divide by our volume in liters. 250 milliliters will be equal to 0.250 liters. So we can see our grams of NaCl cancel, and we're left with moles over liters. So our answer here should be 0.100 molar sodium chloride solution, or 0.100 moles per liter is another way to write that. Either capital M or moles over liters would be the correct units. If we know the molarity of a solution, that will be our link between the moles of a substance and the volume. Molarity has units of moles per liter, so we can use it as a conversion factor. Consider a solution that's labeled 1.20 molar NaCl. What relationships can we write? We could say that there's 1.20 moles of NaCl per liter of solution, or we could say that per 1 liter that solution contains 1.20 moles of sodium chloride. So molarity is a lot like density, where density was our link between mass and volume. Molarity is our link between moles and volume. So imagine we're doing a reaction and we need a certain number of moles of sodium chloride for that reaction, but we're starting with a sodium chloride solution and not the solid. How many milliliters of 0.25 molar sodium chloride solution must be measured to obtain 0.100 moles of sodium chloride. So we need to figure out what volume in milliliters we would actually need to measure out that would contain 0.1 moles of our sodium chloride. So we need to start with what we are given. Now it looks like we're given two things, but our 0.250 molar sodium chloride, that's our conversion factor. That's going to be our link between volume and moles. Anytime you see a capital M, you can cross it off and write moles per liter because that's what it is. So instead we're going to have to start with our moles, which is 0.100 moles, and then we're trying to determine volume, so we're going to have to use our conversion factor of molarity. The number is always with the moles, so that's going to have to go in the denominator, 0.250 moles per liter, and then lastly the problem asks for the number in milliliters. So 1 liter is equal to 1,000 milliliters. If we go back and check, our moles should cancel, our liters should cancel, and this time we're just left with milliliters, which will tell us our volume of solution, and our answer should be 400 milliliters is what we would need to measure out in order to obtain that number of moles. Let's try another example. A student measured 175 milliliters of 0.25 molar HCl solution into a beaker. How many moles of HCl were in the beaker, and how many grams of HCl are in the beaker? We know that our volume is 175 milliliters, and our concentration is 0.25 moles per liter. So anytime we see capital M, we can cross that off and instead write moles over liters. That'll help remind you that that molarity is your link between moles and liters. So starting with 175 milliliters, in order to use our molarity, we're going to have to convert milliliters into liters. There's 1,000 milliliters in 1 liter. And then using our molarity, we know that it is 0.250 moles per liter. Our liters will cancel, our milliliters will cancel, and this will tell us the number of moles of HCl in our solution, which is 4.38 times 10 to the negative 2 moles. And then if we want to find the grams in part 2, we simply have to convert our moles into grams using the molar mass for our substance. The molar mass for HCl we can calculate by using the periodic table, and that should be 36.5 grams per mole. Starting with our moles, 4.38 times 10 to the negative 2 moles, and multiplying by our molar mass, 36.5 grams per every 1 mole. Our moles will cancel and will be left in units of grams, which should be 1.6 grams of HCl. Just like we did in lab, if you need to prepare a solution with a known molarity, you need to determine what the mass is or how many grams of the substance you need to weigh out for your specified concentration. Sodium nitrate can help in easing skin irritations. Suppose we need to prepare 250 milliliters of a 0.100 molar solution. How many grams of strontium nitrate are required? So first we need to write a formula for strontium nitrate. Strontium forms a +2 charge in an ion, and nitrate is one of our polyatomic ions, NO3-. And when we write our neutral formula, then we're going to have Sr NO3 parenthesis 2. Now, remember, we can take our molarity, we can cross off the big M and write moles per liter. So we're starting with 250 milliliters, and we're going to use our molarity to convert to moles. But then finally, we're going to need to get grams. So in order to get grams, we're going to need to calculate the molar mass of our strontium nitrate using the periodic table. And that should equal about 211.6 grams per mole. Now we have everything we need to determine the number of grams we would need to mass out. Starting with our volume, 250 milliliters, we'll convert that to liters, 1,000 milliliters in 1 liter. Now using our molarity, 0.100 moles per liter, and then lastly using the molar mass to find the number of grams, 211.6 grams per mole. Our moles cancel, our liters cancel, our milliliters cancel, and we'll be left in grams. So our answer here is about 5.29 grams of the strontium nitrate that would need to be weighed out. Next, we're going to try a few example problems. What is the molarity of the solution prepared from 783 grams of potassium sulfate in 750 milliliters of solution? So here we're calculating a molarity, so we're going to have to find moles of solute and then divide by liters of solution. We know our grams and we know our total volume. So for potassium sulfate, we're going to have to calculate our molar mass of K2SO4, and our molar mass should be about 174.3 grams per mole. Starting with our grams of solute, 783 grams, we're going to divide by our molar mass, 174.3 grams in 1 mole. That gives us our moles in the numerator, and now we need to simply divide by our volume in liters. 750 milliliters is equal to 0.750 liters. So we're going to plug that in to the denominator, 0.750 liters. Our grams cancel, and we have our units of moles over liters. So our molarity here is about 5.99 molar for this solution. How many milliliters of 0.2 molar aluminum nitrate contains 2.56 grams of aluminum nitrate? First, in order to answer this, we're going to have to write a formula for aluminum nitrate. Aluminum forms a +3 ion. Nitrate is NO3 with the -1 charge. Our formula should be AlNO3 parenthesis with a 3 on the outside. Since we're also determining milliliters, but we're starting with grams, we're going to need to calculate our molar mass for aluminum nitrate. Our molar mass should be about 212.99 grams per mole. And remember, we can take our molarity, the big M, and write moles per liter, so we can remember that's our conversion factor. Starting with our mass in grams, 2.56 grams of our aluminum nitrate. We'll use our molar mass to convert to units of moles, and we know that there's 212.99 grams in 1 mole. Now we can use our molarity to take us from moles to units of volume. We know that the concentration is 0.2 moles per liter. So we're going to put our moles in the denominator, 0.20 moles per 1 liter. And then lastly, 1 liter is equal to 1,000 milliliters. Our liters cancel, our moles cancel, our grams cancel, and we'll be left in milliliters, which should be 60.1 milliliters of our aluminum nitrate solution. How many grams of lithium fluoride would be present in 575 milliliters of 0.75 molar lithium fluoride? Lithium fluoride, our chemical formula would be lithium forms a +1 charge, fluorine forms a -1 charge, so we would have LiF. Our molar mass of lithium fluoride is equal to 25.94 grams per mole. Cross off our big M, write moles per liter, and we're going to start with our volume. 575 milliliters. We're going to convert our milliliters to liters. 1,000 milliliters in 1 liter. Next, we can use our molarity to convert from volume to number of moles. Liters in the denominator and 0.750 moles in the numerator. Next, we're trying to figure out the number of grams of lithium fluoride, so we're going to need to use our molar mass. 1 mole in the denominator is equal to 25.94 grams. Check that everything's in the right place. Moles cancel, liters cancel, milliliters cancel. Our number of grams of lithium fluoride would be 11.2 grams. As you practice in the laboratory, it's fairly straightforward to dilute a solution from a more concentrated one. Also, when we purchase many acids, they come in a very concentrated form, meaning they come in 1 molarity, and those are called stock solutions. For example, HCl always comes to us as 12 molar HCl. Whenever we need to use a different concentration of hydrochloric acid in the lab, I have to go through a dilution process in order to make the correct molarity. We used volumetric glassware, such as volumetric flasks and volumetric pipettes, in order to figure out exactly the amount that we're taking of the concentrated one and then diluting to a specific dilute solution that we're trying to make. When you're making a dilute solution from a concentrated solution, the number of moles that you transfer over of the concentrated solution remains constant in the dilute solution. So if you notice on the left here, this one appears a darker blue because it's more concentrated, and this one on the right here appears lighter blue because it's more dilute. But the number of moles between the two is the same. This is due to the dilution formula, which is often labeled as M1V1 equals M2V2. It doesn't particularly matter what is M1 and what is V1, as long as the correct molarity goes with the correct volume. You might often see it written as M sub D V sub D equals V sub C M sub C, referring to dilute and concentrated. We need to know 3 of the 4 terms in order to solve for the missing one. If we know the molarity of our concentrated solution that we're using, and we can determine what we're trying to make our new dilute solution, our molarity of it, and how much of it we need to make, then we could figure out what volume of our concentrated solution we need to pipette. But in reality, we could solve for any of the missing variables using the dilution formula. How can we prepare 100 milliliters of a 0.04 molar potassium dichromate solution from a 0.2 molar potassium dichromate solution? So since we're making a new solution from one we already have prepared, this is going to be an example where we need to use the dilution formula, or M1V1 equals M2V2. It's important that we can identify which molarity and volume go together, and what is our dilute solution and what is our concentrated solution. Since our 0.2 molar solution is of our greater concentration, this is going to be what we refer to as our concentrated solution. Our 0.04 molar solution is going to be our dilute solution because the molarity is less. And we're preparing 100 milliliters of our dilute solution. So that means that this molarity and this volume go together. Now it doesn't matter what side of the equation we put those on as long as we keep 100 with our 0.04. And we're going to be solving for the volume of the concentrated solution that we need, or V1. We don't know what V1 is going to be or how much of our concentrated solution we're going to have to pipette. So if we rearrange our formula, V1 will be equal to M2 times V2 divided by M1. And we plug in our M2, which will be 0.0400 molar, times the volume we're trying to make, which is 100 milliliters, and then dividing by M1, which is our concentrated solution, 0.200 molar. Notice my units of molarity will both cancel, and my volume will be in units of milliliters because that's what my other volume unit was in. So our V1, or our volume of our concentrated solution we'll need, will be equal to 20 milliliters. So that means that we need to measure out 20 milliliters of our 0.2 molar potassium dichromate solution. And if we're making 100 milliliters total, and you were to subtract off that 20 milliliters that you need to measure out, the difference between those two means that there's going to be 80 milliliters of water used to dilute that 20 milliliters, which will give you your 0.04 molar concentration. Let's try another one. How many milliliters of water have to be added to 150 milliliters of 0.5 molar HCl to reduce the concentration to 0.1 molar HCl? So this is another dilution example. So we're going to be using M1V1 equals M2V2. We can figure out, because 0.5 molar is greater than 0.1 molar, that our 0.5 molar is going to be our concentrated solution, and our 0.1 molar will represent our dilute solution. And we're being told that we're measuring out 150 milliliters of the concentrated solution. In this scenario, we'd be calculating V2, which is the volume of the dilute solution. That's actually the total volume. So that will include the 150 milliliters, plus it'll include the water in there. And we're going to have to work backwards to figure out how much water was actually added to that total volume. So rearranging our formula for V2, we'll have M1V1 over M2. Our M1 will represent our concentrated solution, 0.05 molar, times the volume that we're using of our concentrated solution, 150 milliliters, divided by our new concentration we're trying to make, which is 0.1 molar. Our molarities will cancel, and we'll be left in units of milliliters for our volume. So our volume, our total volume of our solution that we'll make will be 750 milliliters. Now, if we know that we only added 150 milliliters of the concentrated solution, we can subtract that from there to figure out how much water we will have. So 750 total minus the 150 from the concentrated solution, the difference is 600 milliliters, and that's going to be the amount of water that was added to make that concentration.